All right, welcome back to part 3. I think I found my error. So when I was plotting the gust limit load lines for our gust velocities, I rearranged the equation so it was in terms of our wing loading, and I forgot to remove the wing area term on the top. So I was multiplying this slope term by the wing area, which is a large number, so we were getting this ridiculously high slope. So our gust limit line should actually look like this for the parameters that we have for our aircraft. So it starts at 1, and then it has a positive slope, and it's going to go upwards. And for our cruise segment, we really care about where this intersects with our cruise speed. So this would be our maximum gust limit. The negative gust limit line is essentially the same thing, except it's going to be 1 minus these values. So we put that in, and select our data. I'm going to call this gust 50 feet per second as well. See if Excel likes having two with the same name. And we have our negative gust line. So to distinguish these, I'm going to change their color as well. I'll make them black, and I'll have them as dotted lines, or dashed lines. So these dashed lines are our gust speeds. I'm going to change our stall lines to be blue because these are forming part of the boundary. And we're starting to get a better picture of our structural envelope. For the dive gust, essentially the same thing as our cruise gust. So we can just copy over those equations again. I had that saved from before. Now all we have to do is change from our cruise gust velocity to our dive gust velocity. Everything else is going to stay the same. Same thing with this one. Now it's going to be negative, and again back to our dive gust velocity. So we've completed those. We'll add these to our plot. Gust 25 feet per second. I wonder. No. Have to do one at a time. 25 feet per second. X values. Y values. Okay, so we have our gust lines now. So I'll change these as well. Let me make this a bit bigger. Now we have everything we need, pretty much. So I want to format this. These are going to be dive gust lines. We'll make them a little bit different from our cruise gust lines so we can see a difference. And so basically from here, we can draw our structural envelope. So we can choose to just select points and plot them in Excel. That's fine. For now, I'm just going to draw in this by inserting lines, and we'll try to get some explanation as to the general shape. So when we're thinking about our limits, our positive limit at the cruise gust is basically whatever is higher between our design limit load, our positive limit load factor, or our gust line up to the cruise point. So below this intersection here, our design limit load is the highest, so that forms our boundary. But at this point, it's going to start to follow our gust line all the way up to cruise. So I'm going to make this a thicker line. Let's make these really thick. And let's make these red so that we can see what is actually our limit. So I'm just going to keep adding segments. So then from here, it follows this boundary. And then it's going to follow our stall line, and it's going to follow our stall line down to cruise. I wonder if I can create a bent line. Maybe not. Lovely. Maybe I'll just do this. Let's change our stall line. I'll stop it at a speed of approximately 140. $130. Let's just change this value to 135. I could be more precise and actually calculate this. And then we only care for our stall, the section that is a load factor of 1. So that would be around 80 knots. So that's our stall speed. And we can't fly the load factor less than 1. If it's less than 1, it means we're not generating enough lift. So we can't physically fly slower than this. We would just start to stall and fall out of the sky. So this becomes our limit. So if I shrink the region that this is now showing, then I can format this series, and I can just make it red, and that will show our boundary. Good. We do the same thing for our lower stall, and when this intersects with -1 value, I'll move this over a little bit. This intersects with -1, just under 100 knots, so let's go to 90. And we have something around here. 100 knots looks like it'd be too much, so let's try 95. Just to get close. And then our upper limit is when we have that 1.183, so around here. And then we'll make this red. And I'll copy some line segments. What just happened? There we go. So then we have vertical lines for our stall at our lower limits from the intersection of our stall lines and a load factor of positive and -1. So these form the boundary on the left side. So let's continue moving right. From our cruise speed at our maximum gust intensity, we can connect that with a straight line back down to where our dive gust intensity intersects with our dive speed. Now in this half, so between cruise and dive, we have to follow whatever is the maximum. This line that connects our gust lines at cruise and dive, or our maximum limit load factor. So in this case, beyond this intersection here, our load factor takes over. So we'll have this straight line intersect somewhere around here. And then it's going to follow our maximum load factor up to our dive speed. From our dive speed, we'll work our way around. We'll come straight down to our lower dive speed limit, which is down here. And then from this point, we can have another connection, a straight line going from here to the intersection of our gust and our cruise. And we can also have the intersection from our cruise limit line to our 0. So whatever would be greater. And I'll show what that would be so we can get a comparison. So I connect this to our cruise, and I bring this down to 0. Whichever of these two lines is the worst case, so a larger limit load factor, is the line that we would follow. Sometimes they might intersect, depending on where this dive gust line is, so we'd follow whatever one is the lowest. So in this case, the connection between our dive and our cruise is the lowest the whole way. Notice we don't have to follow our lower limit load in this corner, particularly for Part 23 aircraft. We can use this approximation here. So maybe I'll change this color so we know it's something else. I'll make it the same as our dive. So that is a corner that we could adjust, and sorry, that should be going to our dive speed. So instead we can follow this up to our cruise gust, our negative cruise gust, and then we're following that cruise gust line back down to our negative design limit load, and then we have one segment left, and that's connecting our stall line and the intersection of our gust limit line with our negative design limit load. So for this aircraft, we end up with a structural envelope that looks something like this. The last step would just be to go around and label all of these values and then actually calculate what these intersection points are, just root finding between our two functions that we have for each intersection. I'll add another line just so we can see in here how I'm connecting our dive and cruise at the top, because sometimes that's not so obvious. So this line over here is following essentially the line connecting our intersections of our dive and cruise gust velocities. So that's pretty much it. We have our stall speed, our positive stall speed. Maybe I'll label these so that can be more clear. Call this VS plus, so that's our positive stall speed. We have our VA as our maneuvering speed. We have our cruise speed. And we have our dive speed. The last one we can add if we want is our negative maneuvering speed, VG, which would be right down here. So that's the structural envelope. Now, one last thing I want to look at. If I move this, does it move? It's good. So everything's actually in the figure now. I'm going to look at what happens when we change our wing loading. So how does that affect our structural envelope? Now, if we think about our cruise and dive conditions, would change with our wing loading, potentially, but that would come from our constraint analysis. So within this structural analysis, our wing loading is only going to affect our gust curves. That's where it's being used explicitly, and our stall curves. So let's say our best wing loading is changing. We're going to decrease our wing loading, so that means we'd be more susceptible to gusts because we have a larger wing. So the same gust force is going to cause more acceleration, higher loads. We should see these gust lines spread out. And our stall lines also spread out. So we see exactly that happening. So our envelope would change. Now our maximum load factor at our cruise for our gust intensity for cruise at 50 feet per second would increase from what it was before at maybe 3.3, 3.2, and now it's getting closer to 4, maybe 3.9, 3.8. So having a higher wing loading is going to decrease our susceptibility to gust loads. If I increase it to 40, you can see now that the intersection with the cruise speed is actually below our upper design limit load. So at cruise, we would not need to account for gusts because our upper design limit load is actually greater than what our gust load factor would be. So then we have this more or less perfectly level straight line until we get the intersection with our dive. So having a higher wing loading improves the structural envelope, as in we don't have to design for higher structural loads, so that might in turn reduce the weight the aircraft needs to be. Perhaps some cost savings as well. And we can also see the stall limit lines sort of shrink in. So it seems like our structural envelope is decreasing, but what this really means is that the effect of gust loads on our aircraft with a higher wing loading has less of effect on the actual stresses and the loads that are generated. That's just because our aircraft is heavier, there's less surface area for the gust to affect the aircraft, so it's not as affected. The other way that immediately shows an effect is our CL alpha curve. So the slope of our CL alpha curve, if we change this, now this is calculated based on our aspect ratio and so on. So if we have a lower aspect ratio, we're essentially shallowing our lift curve, so making it less steep. So that will also affect our gust because our a gust velocity is just effectively an increase in the angle of attack. So if our slope is lower, then an increase in angle of attack will result in a lower increase in lift and a lower gust load factor. So if we reduce our aspect ratio to 10, let's say, we start to see these lines shrink in. Now it's not as much of an effect as wing loading, but it does have some effect. So an aspect ratio of 8, increased even further, we have a small aspect ratio. At 6, we almost have the same effect for our gust loading as changing our wing loading on our gust lines. In this case, because we're just changing aspect ratio, it doesn't affect our stall limit lines. So just interesting to look at how different parameters affect your structural envelope. So play around with that, and now you have everything you need to actually create your structural envelope diagram, and you should have something that looks kind of like this depending on your aircraft.